Okay, so thank you, Chairman. Today, I will talk about the standby power-free integrated circuit using MTJ-based VLSI computing for the IoT applications. Okay, so the target is a standby power-free integrated circuit, and MTJ is a very important device. This is a spintronics device, and it's very useful for the energy efficient processing is possible by using this device technology. And this is the name of the contributors, and this project is supported by this program. Okay, this is the outline of my talk. First, I will talk about the background, the motivation of this research. The keyword is non-volatile logic key memory architecture used in this approach. Okay, so everybody know the IoT, Internet of Things, has many potential advantage of these areas. The originally these IoT application is limited. The application field is limited, but recently these application fields increased, extended. Then the processing power is also increased. So the many power is consumed in this IoT application. But the second topic is our energy gap is very serious. The battery capacitor is of course increasing, but the energy consumption in the IoT application is also much more increased. Then this gap is wider and wider. So how to solve this problem? So the energy efficient processing is necessary to realize these kinds of the IoT applications. And several kinds of the processor architecture. You know, the GPU style is very powerful, but it consumes also power. And of course, SoC is very power efficient processing, but it is only limited. Some application focus on. Then the purpose FPGA style is very useful because this is very flexible, but it's much better than the energy efficient style. So if this FPGA is moved to this area, so very attractive. So we focus on the FPGA application to these areas. So my today's presentation is just focus on this, how to realize these areas. And the second serious problem is, this IoT application is not stable. The power dissipation is not stable. So sometimes it's down, sometimes it's up. So the processing is, just processing is started from here, but the power is off. So before power off, we must kick back up to the data. So the processing is stopped here, and so the power is applied again. Then the processing started. So data must be reboosted again. In this way, the processing is sometimes stopped. And we must take a backup and reboosting process necessary. So it takes time and also consumes the power. But if you use it to the non-volatile device, we can quickly recover. So of course the power stage is stopped, but we quickly recover the backup stage, and of course the reboosting process is also limited. So in this way, these kind of red lines are much earlier reach to the 100% processing. In this way, it's very useful by using these kind of techniques. And so what kind of this non-volatile device? At present, very fortunately, many kinds of the non-volatile devices. So, but we are focused on these spintronics device. This afternoon, one of our colleague user, Fukami Sensei, is explaining more detail about the spintronics device. and its possibility. And so we just explained it kind of very good scores. How about the access speed is destructible read and light endurance and the scalability? It's very wonderful. So we use this kind of device as logic applications. And this device is two-stage, two kind of state, and 0 state and 1 state. And there are two major styles, 2-terminal, 3-terminal devices is possible by using this device. And the logic key memory architecture we explained. Mitra Sensei also explained this logic and memory, the bottleneck problem is very serious in the computing. Then so logic key memory architecture is very useful and very effective to realize this kind of, to solve these problems. This is a conventional architecture. Conventional architecture is logic part, memory part is completely separate. Then this kind of data transfer bottleneck happen. So this is consumes the power, and the limit is the speed. But by using the non-volatile device is just put on the CMOS layers. Then we can smoothly connect, transport to the data. So it's very useful to realize that we can solve this data bottleneck problem by using these architectures. And the spintronics device is really suitable to realize this kind of the logic memory architecture. Then it is good collaboration, the spintronics device and the logic memory architecture. Then I focus on this kind of architecture by using the spintronics device. Okay, so this is the VLSI processor architecture. The first generation non-volatile VLSI processor, this kind of the data flash on DRAM is replaced to the large scale spintronics memory, and the flip-flops and the SRAM is the cache memory. It just change to the non-volatile one. This is the first generation approach. But as a second generation, we are focused on this kind of the okay, so this is a general purpose logic, and this is logic memory structure style is used to realize this kind of part. So the silicon area is a little bit reduced by using these techniques. So I will show you some concrete example concerning these topics. Okay, so I will show you the non-volatile FPGA, field problem gate arrays. Okay, I'm just quickly overview the field problem gate array. The field problem gate array is, for example, this is half-order circuit schematics, and the circuit schematic is this is explained this kind of the truth table. The truth table is directly realized in the FPGA. So in the FPGA, this is explained this truth table. So if you can write a truth table, so you can realize any type of the logic gate. And okay, so if you use the non-volatile FPGA, the memory part is changed to the non-volatile one. So there are two major blocks. One is a logic element LE, and the other part is a routing switch RS. Both part is necessary to the storage element. This storage element to change to the non-volatile one, then the non-volatile field problem gate array is realized. So okay, so how to realize this kind of elements? We first focus on the lookup table. Lookup table circuit is consists of these kind of structures. These are two kinds of selector. This is one. This selector is the read part. This is read tree, and this is storage part. So of course, the storage part is changed to the non-volatile one, But the conventional field lookup table is a SRAM type cell. So it consumes many transistors, 8 transistors, and of course, to change the number to 1, the 2 number devices necessary to realize this kind of the storage part. But our approach is only 1 access transistor and 1 MTJ. This is semi-trans device. So this looks like a DRAM structure, only 1 access transistor and 1 storage device. So in the sensor amplifier part is only 1 sensor amplifier. By using this configuration, we can great rejection is possible to realize the number of FPGA. Okay, you can see this is graph. Okay, so our approach is this green lines, the start position. You can see okay, this circle is this is a conventional volatile FPGA. This is the row axis is the number of the input. The input is increased, then of course the number of transistors is increased. But the conventional non-volatile FPGA is more transistors necessary. But our approach, the number of transistors is reduced. It's very important. We are put on the additional functionality, non-volatility, but the number of transistors is reduced. This is very important point to realize this our normal logic memory architecture. The second point is the selector. The same name selector is necessary, but we share this selector, only 1 selector. So, okay, this is more concrete circuit, but I will skip this detail, but we can get the result. This is the proposed, the number of transistor is more reduced because we can skip this kind of selector. And we can additional some controller logic, but very small amount. So we can total number of transistors reduce. And the most attractive part is our new approach is we don't move the data because usually the shift operation is a very important function in the lookup table circuit. But our approach, you don't move to the data because light energy is very big in the spin-trans device. So we don't move. Then we can get this result. Okay, this is a blue one. Okay, this is the conventional volatile FPGA, the lookup table. And if you can change the normal type 1, this is a conventional architecture. But if you frequently light operation down, then the energy is very much increased. But only one time, so this part is before power off, then only one time is light. So of course the energy is great rejection. But our approach, we don't move to the data, then we can great rejection is possible too. In this way, the architecture is very important. So of course, the circuit style is also important, but at the second step, we should consider the architecture, how to access or how to manage the data. So this is one example of this approach. Okay, the VLSI CAD environment is very also important. We just quickly overview our system is also the logic synthesis, the circuit simulation, the layout is also prepared to realize this kind of FPGA, the non-volatile logic circuit style. This is some example. Okay, so this white circle is the standard logic, the CMOS only based realization, and this is non-volatile, some part. This is double height size is also fitting up. So this kind of the automatic design style is also prepared. And this is the lineup of our succeeded chip families. I have some this kind of for example, the CTM RAM is also realized, and the TCAM, and this is random logic anyway, the main type of the spintronics-based VLSI also succeed. Okay, so finally, I will conclude my talk. Okay, so in my presentation, I will show you the most MTJ hybrid circuit under the novel storage part is used to realize the MTJ, magnetic tunnel junction device is used to realize. And the key technologies I explained are non-volatile lookup table design, and also the CAD tools. CAD environment is also established in our approach. And so by using these circuit techniques, we can realize the ultra-low powered IoT application paradigms. And finally, I will conclude here. So this circuit technique is not only to use the present computer design, but also the brain-inspired VLSI. It's very important because brain-inspired computing also consumes many wires and many data and logic operation. So the new circuit technique is important. So these kind of non-volatile device techniques is also very useful. Especially we have more breakthroughs necessary to realize these kind of brain-inspired computing. So these kind of circuit techniques is also important. So thank you very much.
Yes, that's very interesting, especially this slide on brain-inspired. Of course, we're going to talk a lot more about neuromorphic computing in the symposium. Now, in relation to the previous presentation by Subhasish, do you plan to build up the magnetic memory in the third dimension above the silicon?
Of course. Okay.
But
yes.
If so, then you would not need transistors blended into the third dimension.
Yeah.
So it seems like maybe that would not be so easy to achieve. And so let him ask the question. I think that's
but yeah, I think as a first step, it's very important to the conventional standard CMOS only based realization put on the MTJ film. So this is a very important first step. So we first focus on these kinds of course, in the future, of course, with three-dimensional stacked structure is also very attractive. So we learn more about this one.
Thank you. Can I ask a question on one of the slides? Okay. Can we go to slide 16?
16, okay.
Very impressive. I just wanted to understand, no, 16. No, 18. I'm sorry.
Oh,
it got
okay.
caught up. I thought it was 6. Okay. Okay. So when you get the 100x benefit, the 99% benefit, right?
Yeah.
Was there an assumption about how often you're in the off mode versus on mode? I'm assuming you're getting the benefit because you don't have to do checkpointing. Is that a correct statement?
Okay. Yes. Okay. Okay. Our this is proposal architecture. In this case, we are free. Okay. So every time we are backup operation down, but the architecture is different. Okay, it's a 6 input. Okay, 6 input is a 64-bit replacement is down usually, but our approach is only 1 bit is replaced because the output is
no, and this shift register is coming because you are turning it on and off.
Yeah,
that's why, right? So now my question is, let's say that we are in an environment where energy is stable. Okay, so no duty cycling. Okay, let's say, what is the benefit? What is the energy benefit if I never turned it off? Let's say, but still, it's non-volatile and all that. You might have some benefits. Yeah.
Okay, benefit. Yeah. Okay, this is assumption. The cycle is very big. Only the very small amount is. This is IoT application. This kind of style. So in the off state. we can greatly reduce reduction of the energy. So total amount of energy is reduced. So no matter device is it kind of the off state, on stage is quickly changed, and the average power is greatly reduced.
Because for FPGAs, as you know, that if you had name relays, especially for switches, for the interconnects, it might be that one could use name relays for the interconnect switches and then use your MTJs for the lookup tables. That might actually give you a lot of benefit, because there the footprint would be very significantly reduced, and like.
Thank you.
So I will call acronym alerts the NEM relay, a nanomechanical relay. Okay. So do we have some more questions, please? And if not, let's thank our speaker again.